Good morning, students. Last class we discussed about the voltage regulation, efficiency, condition for maximum efficiency, and also different types of losses occurred in the single phase transformer. So now today class we'll go for the another concept, that is the performance of a performance of a transformer, single phase transformer. What is meant by performance is nothing but when the transformer is working continuously, what are the problems associated with that one. That means how the efficiency will be calculated, how the regulation will be calculated, how the losses are calculated, like that. That means performance means to know about the internal behavior of the transformer. That will give some values, some numerical values. Because based on that numerical values, we have to decide the particular transformer is efficiently working or does not efficiently working, right? So go for the topic, that is the performance of a transformer. That is nothing but transformer tests. So two tests are done in the transformer: open circuit test or no load test, short circuit test or impedance test. So now open circuit test or no load test, that means we are conducted this transformer for a step up transformer. The primary side is low voltage, secondary side is high voltage. Open circuit or no load is nothing but there is no load. Load is in the secondary. That means high voltage side is open circuited, and low voltage side is we have to place on the different parameter, different instruments to read the reading of a transformer. It may be a voltmeter, ammeter, wattmeter, right? So what is the main aim of this transformer, this test is nothing but to determine the no load losses, otherwise iron losses. No load loss is nothing but there is no load. That means occurred losses are no load. Iron losses. If it is a load, copper loss also occurring. So here there is no load is nothing but copper losses are negligible. That means remaining losses are iron losses only. So by using this test, we can determine the no load losses or iron losses or constant losses, whatever it may be. And also shunt branch parameters R naught and X naught, right? So this test is conducted at rated voltage and rated frequency. What is the rated voltage? So all the equipments may be connected in the low voltage side. Look at the picture. Low voltage side is nothing but is in laboratory 115 volts and 230 volts. So 115 volts is the 115 volts is the rated voltage and 50 hertz is the frequency. So this test is conducted rated voltage and rated frequency. Look at the picture. Say voltmeter is connected always across the supply, and ammeter is connected in series with the line, and also wattmeter is connected. Wattmeter having four parts, that is M main, line, common, voltage. Voltage is again connected to the voltage, and common is connected to the line and this one, and main is connected to the main, and line is connected to the ammeter. In some textbooks, ammeter is connected in place of wattmeter and wattmeter is connected in place of ammeter. There is no problem. And secondary side is open circuit. Now what is the procedure or what is the execution of this test is nothing but switch on the supply by first of all put the variac or single phase auto transformer in minimum position. Switch on the supply by varying the variac or single phase auto transformer slowly. Put the rated voltage on the voltmeter. That means voltmeter will source the 115 volts. According to that 115 volts or rated voltage, note down the readings of ammeter and wattmeter reading. Ammeter reading will gives the no load current I naught, and W wattmeter gives the no load losses, no load core loss or iron losses, WOC, and voltmeter reading VOC. So by using these three values, we can determine the shunt branch parameters, that is R naught and X naught, and also no load current I naught also. So look at the theoretical calculation. We know the core loss or no load loss, WOC is equal to VOC IOC cos pi naught. We know the values of V naught, I naught and WOC. Therefore, determine the no load power factor cos pi naught is equal to WOC by V naught and I naught. From that power factor, no load power factor, we have to determine the watt-full component of no load current, and so another one, that is I mu or IM, that is I naught cos sin pi naught. Once you have to find out the cos pi naught, easily determine the sin pi naught and determine the both currents, that is nothing but watt-full current or core loss current or magnetizing current. After find out the watt-full current and magnetizing currents, we have to determine the shunt branch parameters R naught, X naught by using below formulas. So R naught is equal to V naught by IW and X naught is equal to V naught by I mu. So these equations are also discussed in the before classes, that is transformer on no load topic. So next one, short circuit test. As usual, short circuit test or impedance test is also conducted at low voltage side, and this test is also conducted at rated current and rated frequency. Whereas in open circuit test is conducted rated voltage and rated frequency, but short circuit test is conducted rated current and rated frequency. And what is the main aim of this test is nothing but to determine the full load copper losses and also series branch parameters R01, R02, X01, X02 and Z01, Z02. What is meant by R01? Equivalent resistance referred to the primary. R02 is nothing but equivalent resistance referred to the secondary. X01 equivalent resistance, equivalent reactance referred to the primary. X02 equivalent reactance referred to the secondary. Similarly, Z01 equivalent impedance referred to the primary, and Z02 is nothing but equivalent impedance referred to the secondary. But after find out the full load copper losses and series branch parameters, so combination of open circuit test and short circuit test. We know the iron losses, we know the copper losses, we know the shunt branch parameters, we know the series branch parameters. Now we have to determine the efficiency at any type of load, and also we have to determine the voltage regulation. Here one thing is we have to recognize it clearly. Here we have to determine the efficiency, that means predetermine the efficiency, predetermine the voltage regulation. What is the meaning of predetermination? Predetermination is nothing but we have to calculate the losses individually. We have to calculate the losses individually. After then we have to determine the input. After then find out the output. Then so determine the efficiency. Right? So look at the figure. So this test is conducted low voltage side as well as high voltage. That means high voltage side, not low voltage side. Open circuit test is conducted on LV side, but short circuit test is conducted on HV side, right? So LV side is open circuited. We have to put one short circuit in between the terminals. So all the equipments, that is all the instruments, voltmeter, ammeter, wattmeter is connected at the primary side, that is high voltage side. So now after connecting the connection of a short circuit test, first of all put the single phase auto transformer or variac is put in minimum position, then switch on the supply by varying the variac very slowly. So put the rated current on the ammeter. What is the rated current? It is, suppose we can in our laboratory the transformer rating is 115 by 230 volts. That means here in short circuit test 230 by 115 volts 2 kVA transformer. Now find out the current. Current is nothing but kVA by voltage, right? So kVA 2 kVA, that is 2000 divided by voltage, that is 230. 2000 by 230 is nothing but 8.69 amperes. So that is the rated current in our laboratory. So put the 8.69 rated current on the ammeter. So according to that rated current, so note down the readings of voltmeter and wattmeter. The voltmeter reading gives the short circuit voltage, and wattmeter reading gives the short circuit power, that is nothing but copper losses. So ammeter reading is ISC, short circuit current, that is rated current. Now go for the theoretical calculation. Generally a low voltage, by applying the rated current is nothing but in the voltmeter we show the very low voltage, less than 20 volts, or it may be 15 to 20 volts. So that is a low voltage at correct frequency is applied to the primary, and it is continuously increased till full load current are flowing both primary and secondary. So need not about this explanation. So put the rated current. So according to the rated current, you are to getting all the readings. So for according to the rated current, the voltage is in very low, that is less than 20 volts. So that's why no load current is very low. So now go for the theoretical calculations. Full load copper loss, that is WSC ISC square R01. From that R01 is equal to WSC by ISC square, and Z01 is equal to VSC by ISC. We know the R01, we know the Z01, therefore X01 is equal to square root of Z01 square minus R01 square, right? After finding the R01 and X01, we have to calculate the efficiency and regulation. Generally, efficiency at any fraction of X is nothing but eta X is equal to X into output at full load by X into output at full load plus iron losses plus X square times of the full load copper losses. Suppose we have to take in the secondary side parameter, that is refer to the secondary. We have to calculate the efficiency, refer to the secondary, that is X. Output means V2 I2 cos pi 2 divided by X V2 I2 cos pi 2 plus iron losses plus X square. Copper losses is nothing but I2 square R02. I2 square R equivalent resistance. So now why? Because copper losses are very square of the fraction of the load, right? And calculation of regulation. We know that regulation is nothing but change in terminal voltage from no load to full load, and it is expressed as full load or no load. So E2 minus V2 by E2 into 100, that is I2 R equivalent R02 by E2 into 100 cos pi 2 plus I2 X02 divided by E2 into 100 sin pi 2. Otherwise, percentage resistance drop cos pi 2 plus percentage reactance drop sin pi 2. Like this, we have to determine the efficiency and regulation by using open circuit test and short circuit test also. Now, why the transformer rating is in kVA? Generally, the rotating machines, I mean DC generator and DC motor and remaining induction motors also, they will express it in kilowatts, watt or kilowatt or megawatt. But coming to the transformer, the transformer rating is always expressed in kVA but not in kilowatt. Why? Because copper losses are depending upon the load current, iron losses are depending upon the voltage. So now both losses, that means total losses, will depends on product of voltage and current, that is VA, volt ampere, but not phase angle. Suppose if phase angle is included, then it is also expressed in kilowatt. That's why The transformer rating is expressed in kVA only. So transformer rating does not depending upon the phase angle. So that's why it does not rated as kilowatt. It will express it in only kVA but not kilowatt, right? So it is very important for 2 marks. So it is independent of load power factor. That's why rating of transformer is in kVA and it is not expressed in kilowatt. Next, all day efficiency. Generally, efficiency is nothing but output power by input power. That is nothing but efficiency in per unit. Otherwise, percentage efficiency is nothing but output power by input power multiplied by 100. We are getting the percentage efficiency. But what is all day efficiency? That means the output is expressed in kilowatt hour and also input is expressed in kilowatt hour. Generally, output is nothing but kilowatt, input is nothing but kilowatt, but multiplied by hours in a day, that is nothing but watt hour, kilowatt hour, kilowatt hour. So therefore, it will give the energy consumption of single phase transformer during a period of 24 hours. All day efficiency is also known as operational efficiency or energy efficiency, and it is determined on the basis of energy consumption during a period of 24 hours only. So therefore, the all day efficiency is defined as the ratio of output in kilowatt hour to the input in kilowatt hour of a transformer over a period of 24 hours. Therefore, all day efficiency equal to output in kilowatt hour by input in kilowatt hour. To find the all day efficiency, we have to know the load cycle on the transformer. For a day, what is the load cycle? From 0 to 0 to 9 hours, I mean morning 6 to 9 hours, the energy consumption is some watt hour, and also 10 to 9 to 12 hours, what is the energy consumption? 12 to evening 6 p.m. what is the energy consumption? Like that, we know the load cycle over a period of 24 hours, then only you can easily calculate the all day efficiency. This is also important for 2 marks and problem also important for this concept. Now go for the problem. Obtain the equivalent circuit of a single phase transformer with a rating of 200 by 400 volts, 50 Hz single phase transformer from the following test data. OC test is 200 volts, 0.7 amperes, 70 watts LV side. SC test 15 volts, 10 amperes, 85 watts on HV side. Calculate the secondary voltage when delivering 5 kilowatt at 0.8 power factor lagging and the primary voltage being 200 volts. So we have to draw the equivalent circuit. First, let us recognize once again what is the open circuit test and what is the short circuit test. Open circuit test is conducted at rated voltage and rated frequency, whereas in short circuit test is conducted at rated current and rated frequency. And by using open circuit test, we have to determine the no load losses or iron losses and also shunt branch parameters R0 and X0. These are the main important for this problem. By using OC test, we can determine the R0 and X0, and also by using SC test, we can determine the series branch parameters R01 or R02, X01 or X02, right? So by using these parameters, you can easily draw the equivalent circuit, right? So from OC test, they given, so this is VOC, IOC, WOC. VOC is 200 volts, IOC is 0.7 amperes and WOC is 70 watts. We know the theoretical calculation of OC test. WOC is equal to VOC into IOC into cos pi naught. So therefore, we already given WOC 70 equal to 200 into 0.7 into cos pi naught. Therefore, cos pi naught is equal to, so 70 by 200 into 0.7, that is equal to 0.5. So cos pi naught is equal to 0.5, that is nothing but pi naught is equal to 60 degrees. Now sin pi naught, sin 60, root 3 by 2, that is equal to 0.866. Now determine the no load components of current, that is wattful current IW, that is equal to I naught cos pi naught, and magnetizing current I mu I naught sin pi naught. So I naught is 0.7 into 0.5, that is equal to 0.35 amperes. I naught is equal to 0.7 and sin pi naught is 0.866, therefore 0.606 amperes. So IW is equal to 0.35 amperes, I mu is equal to 0.606 amperes. From that analysis, we have to determine the shunt branch parameters R0 and X0. R0 is equal to V1 by IW, that is 200 by 0.35, that is equal to 571.4 ohms. And X0 is equal to V1 by mu I mu, 200 by 0.606, that is equal to 330 ohms. From OC test, you have to determine the shunt branch parameters. From SC test, as usual, from SC test, you have to determine the series branch parameters. We know the Z02. Z02 is equal to, they given already short circuit voltage and short circuit current. So VSC by I2 rated current, that is 15 by 10, so 1.5 ohms. And from that Z02 you have to determine the, why? Because in OC test you have to determine R01 X01, that means refer to the primary. Here also you have to determine refer to the primary, that is R02 X02. So from that R02 X02 you have to determine R01 X01. So first you have to determine Z02, and K is equal to transformer ratio, that is V2 by V1, 400 by 200, that is equal to 2. From that Z01 is equal to Z02 by K square. Equivalent impedance refer to the primary is nothing but we have to divide the square of the transformer ratio. Z02 by K square, that is 1.5 by 4, that is equal to 0.375 ohm. And we know the losses I2 square R02, that is nothing but copper losses. R02 is equal to 85 by 100, that is 0.85. We know that Z02, we know the R02. From that R01 is equal to R02 by K square, that is 0.21 ohms. So already calculated the Z01, and now we have to calculate the R01. From these two, X01 is equal to square root of Z01 square minus R01 square, that is equal to square root of 0.375 square minus 0.21 square. So by with the help of calculator we have to determine the X01, that is equal to 0.31 ohm. Therefore the output current is equal to KVA by so voltage multiplied by power factor, that is equal to, and I2 is equal to 5000, so it is a 5 KVA, 5000 by 0.8 into 400, that is 15.6 amperes, right? Now determine the voltage regulation. I2 R02 cos pi 2 plus I2 X02 sin pi 2. I2 15.6 into R02 0.85 into cos pi 2 0.8 plus X02 1.24 into sin pi 2 0.6. By calculating with the help of calculator we are getting 22.2 volts. So E2 is equal to 22.2 volts. Therefore V2 secondary voltage, so 400 minus 22.2, that is equal to 377.8 volts. So this value is nothing but drop E2 minus V2. Now we have to determine V2. V2 is equal to 400 minus 22.2 is nothing but 377.8 volts. Now already calculate the shunt branch parameters and already calculate the series branch parameters. From that we have to draw the equivalent circuit. First supply voltage, that is 200 volts, then I1 primary current, that may be split into no load current and secondary current. So no load current, so that may be split into IW and IC. So those values are also indicated. Now this one R0 and X0. R0 is already calculated, that is 571.4 ohms, and X0 is also calculated 330 ohms. These values are also indicated. Now R01 X01. Already these values are also calculated. We have just put on the equivalent circuit diagram. So this is V2 dash. Like this, we have to determine the equivalent efficiency, regulation, and also equivalent circuit. by using OC and SC tests. Thank you. So next class we discuss about the three phase, that is next concept. So three phase polyphase circuits or three phase circuits. To see this video, please subscribe DBS Talks. Thank you.